All right, hey everybody, welcome back. So we've been talking a little bit lately about Riemann sums. We've been adding up a bunch of rectangles. It's been super fun, very geometric. Today we're going to do something a little bit in the same vein. We're going to be calculating still areas under curves, but we're going to be using a bunch of trapezoids. So watch out. It's a trap. Fantastic, hilarious. Let's move on. So again, Riemann sums, rectangles, cool. Why should they get all the glory though? Why am I only using rectangles when there's other wonderful shapes out there, such as trapezoids? You're probably thinking I'm crazy because trapezoids are complicated, but trapezoids are very nice, as you'll see. I actually prefer them to rectangles. I'm saying, well, trapezoids are greater than or equal to rectangles. Sometimes they're the same. Maybe sometimes rectangles are better, but in general, I think trapezoids will be a little bit nicer for what we're trying to do. If you don't believe me, let's look at an example. So let's suppose that I have some function, 6 minus x squared, and I'm only looking at it on the interval from -2 to 2, and I want to find the area under that curve. Here's a wonderful image of what's going on here. And what I've done here is I've drawn I haven't done it, I made Desmos do this, but I made Desmos graph 4 trapezoids for me. And so hopefully you can see these. They're a little bit different from how you normally think of trapezoids. Normally I think of a trapezoid like this, right? Like on its side, parallel sides, and then these two angles are the same or something, I don't know. But these are trapezoids. They're vertical trapezoids, and they're trapezoids because this length and this length are parallel to each other, right? So those are like your bases of your trapezoid. The distance here is your height of the trapezoid, and I hope you all remember that the area of a trapezoid is 1/2 sum of the bases times the height. And so for this first trapezoid, for instance, what's the height here? The height to be looks like 2 maybe, or sorry, the base. This would be like our first base. That's 2 units tall, and the second base is something like maybe 5 units tall, and the height is maybe 1 unit. And so if I plug all this in here, the area of that first trapezoid is 1/2 times base 1, which is 2, plus base 2, which is 5, times the height, which is 1, and that's like 5-ish. So the area of that trapezoid is 5. I think by symmetry, the area of this one is also 5. And then the areas of these two in the middle are something bigger than 5. I don't know what. I don't really care. But you can calculate these things geometrically, add up the corresponding areas, and get a good approximation for what the area underneath of the function is. Okay, sweet. What if I wanted to use more trapezoids? Well, again, I have Desmos, so I can do this. If I use 16 trapezoids, for instance, I'm going to get something like this. And this, I mean, basically looks like it is the area under the function, right? I mean, if you zoom in, you will see a little bit of daylight. It's not exact, but it is getting very precise, which is quite nice. So are they actually better? It's debatable, but and in some instances, trapezoids are great because they get us to the correct answer faster, meaning that we can use less trapezoids than we would have to use rectangles. In math talk, this is a very fancy thing to say this at your next dinner party that you go to, we would say that the trapezoidal sum converges faster than the Riemann sum, and it converges at a faster rate. Just for a quick visual, I don't know if I can get these to go side by side, but we'll try it. So on the left here, I've got my trapezoidal sums, and on the right, I've got my regular old Riemann sums with a midpoint going on. Let's just hit play. This one, that's too fast. Hold on, that's way too fast. Let's slow that down to 0.05. Okay, here we go. Boom. We'll let the rectangle one go, and then let's let the trapezoidal one go. Which one's converging faster? Which one looks better? I don't know. We're getting more and more rectangles on the right, more and more trapezoids on the left. I couldn't start them at the exact same time, unfortunately, but I mean, it's looking like trapezoid is getting better faster, doesn't it? I don't know. It's debatable. Let's see what the numbers are here. The approximation for the trapezoids is at 18.65, and for rectangles it's 18.67, 18.66 now. Okay, there we go. What do we think the answer is? What's your guess as to what the answer is here? I'm going to guess like 18 2/3. Seems like a good guess. Alright, cool. Okay, well, I don't know if I've convinced you if trapezoids are better than rectangles or not, but it's just another tool that we can use to find the area under a curve. We'll talk more about this in class. See you soon.